Okay, so in today's lecture, we're going to formally define the definite integral and then also prove the fundamental theorem of calculus, which is the major theorem of calculus 1. And before doing so, though, we need to recall what we did in the previous lecture. Namely, we were seeking to find the area beneath the curve of a function above the x-axis and bounded with some closed interval a, b. And how did we do this? We look at a function that is defined on that closed interval, and then we take a partition of that interval as a collection of subintervals. So for example, with this partition here, we would have a is equal to x naught. So then the first subinterval would be a to x1, or x naught to x1. The second subinterval would be x1 to x2, so forth and so on, until we get to xn equals to b, where the final subinterval of that interval would be x sub n minus 1 to xn, where xn is equal to b. So more or less, what this is doing is if we have some curve and we have an interval AB, not necessarily positive now, but let's try to interpret what's happening for a function that is both positive and negative. So we partition this closed interval into subintervals. So for example, we could take x1, x2, x3, and then x4. So then this would be a partition into pieces, right? So we have these subintervals of the closed interval AB. And we're going to say that delta x here, or the change in x, is simply the length of the subinterval. So delta 1 would be the length of that interval, delta 2 would be the length of that interval, so forth and so on, which, as we can recall from the previous lecture, is simply the width of a rectangle that we're going to use to somehow approximate the area under the curve. So then we defined a sum, and in the previous lecture we used upper and lower sums, where we would take the sum of the function's value at a given point, whether it's the minimum or maximum in that subinterval, and then multiply that times the width of that subinterval, which is equivalent to finding the area of the rectangle described by this width and that height. Okay, so in the general form, we're going to just say that for a given interval, subinterval I, if ci is any value in that subinterval, then the Riemann sum, named after Bernard Riemann, is going to be the sum of the rectangles described by that height and that width. So for example, I could choose C1 to be like right there. So then the value for the y would be there. So then the first rectangle that we would look at would be like that. Okay. Now notice that in this case, f of C1 is negative, so it would be a negative height, which doesn't really make sense, okay? You can't interpret a negative area. Area is by definition positive. But still, this general form here, from a mathematical point of view, what is it? How can we figure out what it's calculating? Well, maybe if we take like C2 right there, so then our rectangle would be like that. And somehow it's like trying to approximate that area. And then if we took C3 to be like there, so then the height would be like there. I'm just picking the midpoints now. because it's different than what we did last time, but it's in this more general sense. And then C5 would be like there, so. So in a sense, that's what we're doing, but now these are like negative areas, and it's not describing an area, but it's more of an abstraction of what that formula is doing. Okay. Now, what happens as we choose, if we refine our partition to have smaller and smaller widths of these subintervals? Well, as we saw last time, sometimes this will converge. So in particular, if we let this denote the norm of the partition, which is the max of the lengths of the subintervals, and we want those subintervals to become smaller and smaller, what happens is we get smaller and smaller subintervals, which means we're getting more and more rectangles. So this is what we did last time, and that's when we look at the limit of the norm of the partition. If we want the lengths of those subintervals to be very, very small or go to 0 for this sum, sometimes this sum will converge, and we saw that last time. Right? The smaller the intervals are, the subintervals are, the more rectangles we have, the better approximation to what we had last time as the area interpreted under the curve above the x-axis. But in this more general picture, we also have these negative rectangles that are kind of accumulating here. So in the general sense, this limiting process is not always going to be well defined in terms of area, but it's still going to tell us something, and that's something we're going to get to when we prove the fundamental theorem of calculus. Now, if this converges, so if that converges, then we're going to say that the function f is Riemann integrable on that closed interval. And for the purposes of this class, we're just going to say integrable. Okay, so if that limit exists, like if this sum converges to some numerical value, we're going to say that the function is Riemann integrable, and we're going to introduce the notation that that limit, as the lengths of the partitions go to 0 of the sum, I is equal 1 to n, ci, the width of the rectangle, we're going to say that that's going to be equal to this notation. B f of x dx. Okay, now this is the notation used for the definite integral. So that is the definite integral. I was going to point. This is the definite integral. Okay. Now, this notation takes a moment to explain. This is like an elongated S to represent a sum, but the reason why we're not using sigma when we're using this elongated S is because it's technically not a sum. It's a limiting value. This limit of these sums tends towards something. So it's a limit sum in a sense. And that's why we're not actually using the sum, because sums by definition are just finite additions, where this is some limiting addition, right? Now also the A and B, so these are the limits of integration. So A is called the lower limit of integration. Okay. And then B is the upper limit of integration. Running out of room, but that says upper limit of integration. And here, this dx is, the way that I like to think about it is, when you take, suppose all these have the same size, right? When you're taking the limit as the size of those things goes to 0, the change in x becomes this small differential. It's a tiny change in x. It also tells you what variable you're integrating with respect to. So this determines your variable of integration. Okay, so that determines your variable of integration. Now, as we saw in the last lecture, evaluating these limits can be somewhat cumbersome, right? It took something like 30 minutes just to set up the Riemann sum for a linear function, and then once we had that set up, we evaluated the limit, we saw that it converged. But this is this would suggest that determining these definite integrals of functions is difficult, right? Because it took so long just to do this on a linear function, right? However, we have what's known as the fundamental theorem of calculus, which we will prove now. In particular, I'm going to pause the video and then erase, and then we will give the proof. Okay, so now we're going to prove the fundamental theorem of calculus. Before doing so, we need to recall definitions, so we have the Riemann sum for a given partition is just equal to the widths of each subinterval times the function's value on some element of the subinterval. The definite integral is defined as this limit, provided this limit exists. So it's the limit as the widths of your partition subintervals go to 0. If that converges to a number, we have our Riemann integral or definite integral. Then we have the mean value theorem, which states that if f is continuous and differentiable on AB, then for some c in the open interval AB, the derivative's value at c is equal to the slope of a line connecting the points a comma f of a with b comma f of b. And so now that we have these statements, let's consider the statement of the fundamental theorem of calculus, which says that if f is continuous on the closed interval AB, and capital F is the antiderivative of f on AB, then evaluating the definite integral of f from a to b is equivalent to looking at the difference of the antiderivatives over that on the endpoints of that interval. Now, as we saw in a previous lecture, we learned about antiderivatives. They're just the reverse, right? You're looking at some function and you want to reverse to see what function's derivative gives you what you were looking at. So finding antiderivatives is not as difficult as piecing together every little intricate part of this Riemann sum. So this is a huge statement if it's true, and it is, right? Because it reduces calculating integrals to finding antiderivatives. So integration, definite integration, and differentiation are intimately related in this inverse manner. So in order to prove this, we need to form a Riemann sum first, okay? In order to form a Riemann sum, you need to first partition the closed interval into pieces, right? So I'm going to say, let delta be a partition. So A is equal to x naught, which is less than x1, which is less than dot, 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 less than xn minus 1, less than xn, which is equal to b. Be a partition of that closed interval AB. Okay. Now, the next part of the proof is, it might seem arbitrary, but at least hopefully you will agree that it's true. So let me say next observe that we can say f of capital B minus capital F of A. So capital F of B minus capital F of A, that's like this piece here. So we want to look at that. If we're going to show this equation to be true, we're just looking at that piece. And we notice here that this is the same thing as saying F of the last piece. So xn is equal to B. Okay. But now we're going to do a little trick here and say minus f of xn minus 1 plus f of xn minus 1. And then I'm going to say f of x naught. Now, do you agree that that's true? Just take a moment to look at it. In particular, what is the value of this plus this? What does that equal? Isn't that just 0? They're the same thing, right? And then f of xn, that's f of b. Capital F of x naught, that's f of a, so that's the same thing, right? Do you agree? So it's just a little trick, right? Well, instead of stopping there, what I'm going to do is I'm going to keep on doing this 0 addition thing. So then minus f of xn minus 2 plus f of xn minus 2. That's 0 as well, right? And I'm just going to do dot, dot, dot all the way down to minus f of x1 plus f of x1, so dot, dot, dot. And then finally, at the very end, subtract off f of x naught. So really, when I'm looking at this, that's 0, that's 0, everything is 0, that's 0, and then finally, we subtract off f of x naught. So there's f of b, there's a bunch of zeros minus f of a. So there's zeros everywhere in there, right? Which we're allowed to do. We can add 0 as many times as we want, and we're not going to change this equation, right? Okay, now what? What can we say? Oh, well, we're going to use this mean value theorem now. Because f is continuous, right, on AB. Little f is continuous on AB, and then also f, right, so f is the antiderivative of f on AB, which means that f is surely differentiable on AB because it's the antiderivative of f. If I take the derivative of that, I get that on that interval. So I know that capital F is satisfying the hypothesis of the mean value theorem. Well, why is that useful? So by the mean value theorem, there is, y'all can still read that, right? There is, well, maybe I can say the mean value theorem for each I from 1 to n there is some ci in xi minus 1 xi so that f prime of ci is equal to f of xi minus f of xi minus 1 all over xi minus xi minus 1. Okay, y'all can read that. That's like your B and your A, your B and your A. So for each of those sub-intervals, I'm applying the mean value theorem to capital F, and I get that that's true. But what is this saying? This is just saying that f of xi minus f of xi minus 1. This is just this is the width of that subinterval, right? That's the width of the subinterval. Okay. But capital F is the antiderivative of little f, right? So the derivative of the antiderivative just gives you back the original function f. So this is equal to little f at ci. So what do we get? Which implies that little f of ci, the derivative of capital F is that. That is equal to this. So if I multiply both sides by delta xi, I get this equation. This is that. The derivative of capital F is little f because capital F is the antiderivative of little f. And here, I just multiplied both sides of this equation by delta xi, so that's why there's delta xi right there. So then f at little c times the change in xi is equal to this. Okay. So far, so good. Is that okay? It's kind of messy looking, but so far, so good. Okay. So now looking back here, maybe I'll use like green. Look at this. F of xn minus f of xn minus 1. And then the next term would be f of xn minus 1 minus f of n minus 2, right? all the way down to f of x1 minus f of x0, right? You can pair all of these together, like these are paired together, that's paired with this one's paired with the next one, and then at the very end, that's paired with that. So this sum is equal to the differences there, plus the differences there, plus the differences there, plus the differences all the way through. Which means that, and this holds for each of those i's in this difference, which means that f of b minus capital F of a, which is this side, is equal to that difference plus the next difference plus the next difference, which each of those differences look like that. But those differences are equal to that. So this is actually equal to, from I is equal 1 to n of all of those differences. But those differences are really that. So I can just write okay. So what does that mean? So these are just two numbers, right? And over here, we have changes in x to worry about, which means that if I take the limit as the norm of the partition goes to 0 on both sides of this equation, the left-hand side doesn't change, it's a constant. But we have terms that involve the lengths of the partition over here. So this sum again from I is equal 1 to n. Okay. And this constant is going to equal that. Which, if this converges, which it will here, done. So that is the proof of the fundamental theorem of calculus. Okay. Now, again, it's a little messy, so I encourage you to look up proofs of this online or in your textbook, just so you can not have it all jumbled up everywhere. But this is the general idea. You assume that f is continuous and that it has an antiderivative on that closed interval. And then you just apply the mean value theorem using this like somewhat of a trick of a sum. And you get that each of the differences there are equal to the pieces of the Riemann sum. So we know that the difference is equal to the sum of those pieces in the Riemann sum. You take the limit as the norm of the partition goes to 0. The left-hand side stays the same, and the right-hand side is simply that interval. So we have that is equal to that. Now, in the next video, we're going to show how convenient this is when evaluating definite integrals. So I'm going to go ahead and stop this recording and then start another one in a moment.